Hi everyone, my name is Lingling. I'm a PhD student in the Department of Electrical Engineering at Stanford University. Today I'm going to present our recent work on nighttime power generation system using outer space darkness, published on Optical Express. According to the United Nations report, more than 1 billion people in the world live off-grid. Most of them rely on solar energy. However, for lighting purposes, the electrical power demand peaks during nighttime when the sun is not available. A feasible approach to mitigating this discrepancy is to develop a passive system that can generate work during nighttime. To develop a sustainable energy source, much of the energy research has to do with converting heat into useful energy, such as electricity. To that end, you would like to have a high temperature heat source, and its temperature should be as high as possible. The sun at 6,000 Kelvin, for example, is an ideal heat source during the daytime. You would also, on the other hand, like to have a cold sink. We expect its temperature to be as low as possible. Most of the energy conversion we use today uses the Earth as a heat sink, where the temperature is about 300 Kelvin. At night, however, the sun is not accessible as a hot source to drive a heat engine. On the other hand, there does exist a low-temperature cold sink, the universe, which is maintained about 3 Kelvin. Using the ambient air surrounding the Earth's surface instead as a heat source and the space as a cold sink, then would allow one to drive a new kind of heat engine and generate electricity at night. A proof of concept experiment developed a device that couples the cold side of the thermoelectric generator to a black body radiative cooler. This black body radiates heat to the cold of the space, and its hot side is heated by the surrounding air. This temperature gradient formed between the cold and hot side is converted into electricity by this thermoelectric power generator. This enables electric power generation of 25 milliwatts per meter squared at night, and this is sufficient to light up an LED. In order to get high power density, we need to maximize the cooling power on the cold side and therefore lower down the cold side temperature as much as possible. In this experiment, the cold side temperature is 5 Kelvin below the ambient temperature. Although this demonstration of nighttime power generation is remarkable, it is not sufficient to fulfill the energy demand of many applications. We need to improve the power generation density to a level of 1 watt per meter squared. In our work, we achieve this goal from two pathways. First, we design a radiative cooler. Its emissivity is specially designed to send more heat to the outer space. Second, we optimize the heat transfer conditions to reduce the parasitic heat loss and improve the thermoelectric conversion. By systematic optimization, we achieve over 1 watt per meter squared power generation density for rooftop applications. We also prove a 3 watt per meter squared performance that approaches the thermodynamic limit by using a high ZT material. With a state-of-the-art thermoelectric generator, ZT equals to 6, we get 2.2 watt per meter squared electrical power generation, and this is 2 orders of magnitude higher than the previous experimental result. From the emissivity perspective, the blackbody radiative cooler used in the previous experiment is suboptimal for radiative cooling. It corresponds to this green line on the right and its unity for all wavelengths. The black line here is the major transmission spectrum of the atmosphere. I would like to draw your attention to the 8 to 13 micrometer wavelength range. The sky is almost transparent, and it provides a radiative access to do the radiative cooling. However, at wavelength range where we labeled as red, the atmosphere absorption is strong, and the blackbody emitter is heated up by the atmospheric radiation. Therefore, at a given ambient temperature, the optimal emissivity that maximizes the cooling power should be unity when the radiative power is larger than the absorbed power. Otherwise, it should be 0. At ambient temperature at 300 Kelvin, this is the optimal emissivity spectrum. The yellow region corresponds to strong emission at frequencies and angles where the atmospheric absorption are relatively smaller. The blue region corresponds to zero emission, where the sky is mostly opaque and the downward radiation is intensive. Now we show an emissivity spectrum on a multi-layer structure. The spectral angular selectivity is close to the optimal spectrum as we described on the last slide. On the right side, we show the material composition and thickness of the multi-layer structure that corresponds to the spectrum on the left. Using this radiative cooler, we get the cold side temperature that is 7 Kelvin below the ambient temperature. Now we show the improvement of power density by optimizing the emissivity spectrum. We compare 3 emitters shown at the bottom. Using the same parameters as the experimental setup, we compare the output power density Pmax of the 3 emitters as well as the temperature difference between the radiative cooler and the ambient environment. The red dots correspond to the experimental results, which we can faithfully reproduce. And we also show that this power generation performance is improved compared with the black body radiative cooler for all ambient temperatures. Now we look at the heat transfer conditions. We first studied this hot side convection coefficient. It evaluates how much power is harvested from the ambient environment to the system for a given temperature difference. We calculate the power generation density for different convection conditions. At the black dot, H sub H corresponds to 100 watt per meter squared per Kelvin, and the power density is 2.2 watt per meter squared. In our optimal system, we use the heat sink to approach the high convection coefficient on the hot side. On the contrary, the cold side convection coefficient evaluates how much power is lost to the environment for a given temperature difference. We calculate the power generation density for different convection conditions. At the black dot, H sub C corresponds to 0.001 watt per meter squared per Kelvin, and the power density is 2.2 watt per meter squared. In our optimal system, we use a vacuum chamber to approach the low convection coefficient on the cold side. Now we consider the thermoelectric figure merit CT value, which evaluates how much thermal power can be converted into electricity. We calculate the power generation density for different ZT. At the black dot, ZT corresponds to 100, and the power density is 2.9 watt per meter squared. In our optimal system, we use the high ZT material to generate more electricity. Having optimized the nighttime power generation system, we naturally ask the question, what is the thermodynamic limit? We solve this problem by replacing this thermoelectric power generator with a Carnot engine and solve for the same maximum power density. Using the same principles as before, we get an optimal emissivity spectrum. We compare its power generation performance with other 2 emitters. At ambient temperature of 300 Kelvin, the Carnot engine power density is 6.4 watt per meter squared. Therefore, by the load matching condition, the upper bound for the thermoelectric power generation on the load resistor is half of that obtained by ideal Carnot engine, which is 3.2 watt per meter squared. This verifies that our result of the optimized system are close to the Carnot limit. In comparison, the optimal nighttime power generation system that produces 2.2 watt per meter squared outperforms most of the ambient energy harvesting techniques, such as human body, and is comparable with other ambient energy harvesting techniques, such as wind. To conclude, we optimize the power generation system for maximal light power generation, and we proved this thermodynamic limit for nighttime power generation. This is our publication. Thanks for your attention, and I'm happy to answer your questions.